Thank you. As said, I'm Juliette. I'm the new assistant professor at Dartmouth and Syzygies beyond projective space. All of the new results that I'm talking about are joined with Lauren Cranton-Heller, who is now a postdoc at the University of Nebraska, and Marie Serafi, who's a new postdoc at Masters. So before we move the beyond projective space, let's start out. What do I mean by syzygies on projective space? And so throughout this talk, the setup is always going to be that S is some polynomial ring, C is joined to x0 through xn, and M is going to be a finitely generated S model. For this first part of the talk, I want to assume that my ring S has the standard Z grading, by which I just mean the degree of each variable xi is equal to 1. So when I talk about the degree of a polynomial, it's the degree we all know and love whenever we learn about polynomials. And then I'll also assume that M is a finitely generated S module that is also graded. So then, in some sense, the star of the show, syzygies, is kind of, I think of as being a somewhat squashy word, which for me is analogous to looking at minimal graded free resolution. So the star of the show is going to be the following definition. The minimal graded free resolution M is a chain complex it's some chain complex, so not 1, some differential d0 in between, 1, so on, keep it going back, satisfying some properties. And what are the properties? First, I want to assume that the Fi are graded free S modules. So if you'd like to think, each of these Fi's has some minimal generating set, and those minimal generators are homogeneous polynomials of some given degree. Second, I want to assume that the maps di preserve degree. So this first condition here tells me that this is a free complex. Combined, these two tell me that it's a graded complex. Although the graded condition is not so much of an issue, we kind of just arbitrarily change what we mean by degree as we go along to make the second condition true. Third, F dot is exact, except at D0, and the co-kernel of D0 is isomorphic to M. Sorry. So everything is exact except on the left here, and the co-kernel of this map is M. So we might often write this kind of as adding an M here just to remind ourselves that we're taking the resolution of M, and that when I write it this way, even though M isn't part of the data, now it's exact. And the last condition, so this is free, this is graded, this is resolution. The last condition is minimal, and the minimal condition tells me that the image of my differential di has to land in the maximal ideal x0 through xn times fi. So right, essentially, if we wrote down these differentials as matrices, because I fixed generators on each side, this condition would tell me that every entry of that matrix has positive degree. It can't have any constants. If you had a constant in that matrix, it turns out you essentially don't need it. You could quotient out by the subcomplex that generator corresponded to and get a smaller resolution in some sense that still satisfies the first three properties. So this is a minimal graded free resolution. Let's see an example. Such a thing. So to give an example, right, I have to give you a module. Let's look at the module C adjoint S cubed, S squared T, S T squared, and T cubed. This is going to be my M. Right now, it's only presented as a subring of the ring on a polynomial ring on two generators. So what is this module over? Well, let me think of it as a module over the ring C adjoint X naught, X1, X2, X3, where X0 acts by multiplication by S cubed, X1 by S squared T, and so on. So this makes M into a graded S module. Let's try to find the minimal graded free resolution of it. Well, I want to find something whose co-kernel is M. So I start by writing M. And I need some free module that surjects onto M, but lo and behold, I picked one variable for each generator, so I can just surject S onto M. This map sends X0 to S cubed and so on. But now I have a kernel because I have some relations here. And well, the relations are exactly going to come from saying things like, well, if I multiply S cubed and T cubed, that's the same thing as multiplying the middle two. So in particular, it turns out the kernel is going to be three-dimensional. Let me look at my notes to make sure I get my signs correct. But to be checked, this is going to be X0, X1, sorry, X0, X2 minus 1 squared, X1, X2 minus X naught, X3, and then lastly, X1, X3 minus X2 squared. So these are the three generators for the kernel of this first map. Notice that each of these is a degree 2 polynomial. So to keep track of that, I'm just going to put a little parentheses -2 to kind of keep track that here all my generators live in degree 2. This map is now going to have a kernel itself, and we continue to check that the kernel is in fact generated by two things. The kernel is generated by X3, X2, X1, X1, X2, X1, X0. These look linear, so you might expect me to put a -1 here, but because this was a -2, I actually want to put a -3, so these land. When I take something of -3 and I multiply by things of degree 1, I want to get. So this, lo and behold, is the minimal graded free resolution of this module M over the polynomial ring S here. If you've never seen where this comes from, I'd recommend you think about how you can recognize these three equations as the determinant of some matrix, and then say that these relations exactly come from a clever form of Laplace expansion from that determinant. So this is an example. And the main question that I kind of want to ask in this talk is, how does geometry affect the shape of syzygies? And by syzygies, I essentially mean minimal graded free resolutions, or maybe I mean the entries of these matrices or the kernels of these maps, all essentially analogous data. So what do I mean by shape? I mean how long, so what is the possible length of this resolution? So what is the length? How kind of many different generators do I have in each degree? Which if I had many generators, it would kind of grow out this way. I often refer to that as the height, so the length, the height. And the last two things that maybe I'm stretching the word kind of shape. Do these things exist? We wrote down one, but that doesn't mean they exist. And if they exist, are they unique? So we want to talk about length, height, existence, and uniqueness. And you might be asking at this point, well, you said, how does geometry affect these things? But there has been no geometry in this talk so far. I've only been doing commutative algebra. And well, I'm sure most of you are aware where the geometry might come in, but let's sketch the picture carefully. Well, we're not beyond projective space. We're still there. So on the one hand, on the geometry side, what I mean when I talk about geometry is that I have projective n space. And projective n space, I think most of you are aware, right? When you think of kind of as being equivalence classes of tuples, x0 through xn, equivalent to lambda x naught, lambda xn, for some non-zero lambda and c star. Right? These are kind of the points of Pn. We could have a this action has some fixed locus, right? We could call this fixed locus f, which in this case is just x0, 0. So kind of the only fixed point of this action is the origin. We have subvarieties of projective space. And we also have things, if we want to be fancy, like coherent sheaves on projective space. And the reason we want to look at things coming from this sort of world is because they will exactly be a source of finitely generated graded S modules. So what do I mean? The fact that I'm working on Pn exactly means I have a polynomial ring x0 through xn lying around. And in fact, since its projective space comes from this quotient of this group action, it's not just a polynomial ring, but it's a polynomial ring with a grading. We have the z grading on this polynomial ring, which is what I introduced before. Since we have a fixed locus that corresponds exactly to the origin, we have kind of a distinguished ideal, namely the ideal of that fixed locus, B, x naught and xn, the unique maximal homogeneous ideal, often plays a special role. We already saw it in the definition of a minimal graded free resolution. Right, if we have a subvariety of projective n space, we can associate to it its defining ideal, or its defining homogeneous coordinate ring, S mod IX. And if we have a coherent sheaf, we can associate to it some graded module n. So this is the standard geometry algebra dictionary that we all know and love. And the name of the game is to say, okay, if I take something with geometry here, it gives me an algebraic object. What of the geometry does the minimal graded free resolutions or the Syzygies see of my object? So let's see the answer here. So from now on, I'm always going to assume that I'm looking at things in this correspondence. So if I write an M, I'm going to mean it comes from some coherent sheaf F. And if I write F, I mean it comes from some graded module and vice versa. The first thing, well, you probably want to know that minimal graded free resolutions exist. And lovely Hilbert, in his work on this 14th problem in 1890 that we've already seen quite a bit about, invariant, proved that in the setting, minimal graded free resolutions exist, are unique isomorphisms, and the length of such a resolution, if I'm coming from an object on Pn, is bounded above the dimension of Pn, meaning it has length at most n. Okay. So this almost immediately answers two of the questions, or three of the four questions on what's the possible shape. Hilbert says they exist and are unique, and the length is bounded in a nice way by the dimension of my ambient projective space. And in fact, this is about as good as you can do. If you're not, If your thing is nice, you can maybe get a little bit better, but in general, bounding by the dimension of your ambient projective space is all you can do. So let's see in this example, can anyone point out where this module comes from in geometry?
Twisted cubic?
Twisted cubic. Is that a question?
It's a rational normal column of the case. For T equals V.
What?
It gives the rational normal column. It's like third dimension.
So this gives the rational normal curve, yes?
Yes.
Yes, so this example here, right, is exactly the embedding of P1 into P3 by the complete linear series O of 3. So this is the twisted cubic. As I presented it here, this is presenting a section ring abstractly, and finding this first Syzygy module here was exactly finding defining equations in projective free space. So when you think about what are Syzygies doing, they are capturing defining equations and relations amongst sections and relations amongst relations and so on. And notice here that this has length 2, which is smaller than 3, which is because this curve is arithmetically column-to-column. So great. 3 of the 4 done. That's good. My work is easy. So now, how do we control the height? So what degrees my generators appear in? Well, to do this, we need to jump forward in history about 70 years. 1966, when Mumford gave us the following definition. That if F is coherent sheaf, n, and D is some integer, we say F is D regular if and only if everything was nice, and now it's about to be a little bit less nice. The ith cohomology on Pn of F twisted by D minus I is 0 for all I greater than or equal to 1. So by, essentially it says we call something D regular if D is a sufficiently high twist, so all the higher cohomology vanishes. It's somehow a definition meant to effectivize their vanishing. And Mumford cared because he wanted to make nice things like mod covert schemes and quote schemes and create things like this. And this definition is pretty nice, although I'll say if you want to work with it, it's kind of a hard computing cohomology of coherent sheets. Difficult by hand, but it turns out that this definition is exactly what one needs to bound kind of the height of minimal graded free resolutions. What do I mean by that? That's backwards, sorry. I mean, we get the following theorem. 20 years further into the future, Goethe, in 1986, is the following are equivalent. The first one is that the sheaf F is D regular in the sense of Mumford's definition, so the higher cohomology twist of F vanishes when you twist by D minus I. Secondly, the Syzygies of M, so if you resolve the module coming from F, so take the section module F, that gives you some module M, have degrees less than or equal to D. That's a little bit of a lie. Really what I want to say is at each step of my resolution, less than or equal to D plus I. That's step I. So if you look at the first I steps of my resolution, the entries in that matrix should have degree D. Okay. And lastly, if you take your module and you look at the submodule generated by everything whose degree is larger than D, this is a new module. Notice it gives you the same sheaf as M because they agree in high degree. But this has a linear resolution, by which I mean all the entries in the matrices when you write down the minimal graded free resolution of M truncated at D are linear forms on the nodes. So in some sense, this resolution has the simplest possible degree. It's all concentrated in one degree. It has smallest possible height. So this is, I think, a lovely theorem because A, this second result here exactly controls kind of what degrees appear in a resolution in terms of the geometry of our sheaf. Also, computing syzygies or minimal graded free resolutions, even better, computing minimum free resolutions of this truncation are much more computationally effective in general than computing sheaf cohomology. It's much easier to ask someone to write down a resolution, or even better, ask Macaulay 2 to write down a resolution than it is to ask a friend to compute sheaf cohomology. Or at least my friends. I don't know. Maybe, maybe some of your friends really love sheaf cohomology. So this is great. I would say these two theorems with this definition essentially answer the 4 questions we're given about kind of the length, the height, the existence, and the uniqueness of free resolutions on projective space. You might ask, can we do any better, right? This is kind of, maybe you are complaining and saying, this isn't much geometry here somehow, right? Like all we're saying is, if the cohomology vanishes, somehow we get some bounds on homological things. And it turns out, at least in the case of curves, there's an entire beautiful story saying the syzygies of curves connect to kind of this, the geometry of the curve. And let me give you one taste of such a result. So this is a theorem. Originally proven in one direction by Green in 1984/85. It was conjectured officially by Green, Lazarsfeld, 86, and finally proven in this form by Hein and Lazarsfeld, 2015. I don't think this was Rob Lazarsfeld's thesis project, but I think this is something about don't get stuck on your early career projects for too long. Coming back to it 30 years later. So what does the theorem say? It says if C inside of Pn is a smooth curve, and the degree of C is sufficiently big, then the DI matrix in the minimal resolution at C has linear entries if and only if. So it's saying exactly which of my differentials have linear entries, if and only if I is between 1 and n minus the gonality of C. So n is the dimension of my ambient projective space, and the gonality of C is the minimal degree of a branched cover of P1. Look at all maps to P1 that are branched covers, look at their degree, you take the smallest such number. That's exactly the gonality of C. I'll point out something interesting here, which is that as I defined it, syzygies don't capture things about geometry. They capture things about the geometry of a variety embedded into projective space. So really it's about the geometry of a variety with a line bond. That said, the gonality of C is intrinsic to your curve. It doesn't depend on the embedding. So if you gave me a curve of large enough degree and you gave me its minimal graded free resolution and you said this curve lives in P10, I could tell you something intrinsic to the geometry of that curve, which is somehow I find quite shocking. And this is part of a much longer and beautiful story. For example, you can look at Poisson's theorem, which describes the relationship between the syzygies of a canonically embedded curve and the Clifford index of that curve. Look at how this relates to moduli spaces with work of Parkish and Kemeny. It's an entire beautiful story about how, for curves, syzygies capture intrinsic geometry. And so this is where I want to end the in PN. What do I mean when I say syzygies capture geometry? I mean, in some sense, we know minimal graded free resolutions exist and are unique. Their length is bounded in a nice way by the dimension of the ambient space. And the height is controlled, the number of degrees we get in each set is controlled by something like sheaf cohomology vanishing. And in fact, sheaf cohomology vanishing is determined by the resolution. And we get nice results about things like curves connecting the geometry. Are there any questions at this point before we move bravely into the world beyond projective space?
Large enough so you have bounds?
For large, yes. So Ein and Lazafeld's original paper in 2015, roughly, it's not there, but roughly GP.
Okay.
Parkish and Kemeny is a conjectural thing that's roughly linear in G. And then this last fall, you and Clark gave what essentially should be the correct linear bounds on G. So it's somehow like G times the degree of something. Or different classes that count. Okay, other questions? Okay, so yeah.
Can you explain the this height again in the example? I have not quite understood what this height of this is.
Yeah, so by height, I essentially mean what are the possible degrees that appear in these matrices? And why I say height is because, well, if you were to, here I only had 1 degree showing up 2, but you could imagine where I had quadrics and cubics, right? And then I'd have something like s minus 2, and here I do s minus 2. So kind of, when you write them, they kind of span out this way. So by height, I just mean the number of minimal generators of a given degree at each step.
So these height 1.
Yeah, essentially. Yeah. Height is maybe an unofficial term, but I'm being, yeah. Yeah.
Maybe just missed the SC. What was the module?
So SC is the coordinate range of your curve embedded in a PN. So S mod the defining. So let's move to the world beyond projective space. And for me, beyond projective space exactly means I want to work on toric varieties. So somewhere on one of these boards, right here, we have this dictionary between geometry and algebra. And I want to say, if you've never seen toric varieties, well, you haven't paid attention in the talk so far, because I've done that many times, you have. But for this talk, what you need to know is that we have a similar dictionary between algebra and geometry. So what is the dictionary for algebra and geometry for toric varieties? Well, on the geometry side, I'm going to let Y be a toric variety. What does this mean? For me, I think I want to say this means I take the torus C star to the R. It acts on C to the N plus 1 by some action. It has, this action might have some fixed points. And then, which I'll call F, my toric variety should be thought of as C to the N plus 1 without the fixed locus quotiented out by the action of this torus. So in projective space, right, F was exactly the origin, N was N, and R was 1. I'll leave it to you as an exercise. Realize P1 cross P2 as a toric variety using this setup. Maybe modulo whatever I mean by quotient. So again, if we're in this setup, we have things like subvarieties of toric varieties and coherent sheaves on toric varieties. So this is the geometric side of the dictionary, and it turns out that the algebraic side of the dictionary is almost the same. So what do I mean almost the same? Well, first off, I have a polynomial ring, x0 to xn. Why is that? Well, because I'm working on a large affine cone of c to the n plus 1, so these are essentially my coordinates modulo equivalence class. The action of the group gives me a grading, but now instead of having z, I have a z to the r grading. So somehow the degree of the xi are keeping track of how this group acts. Okay, so now instead of saying the degree of a polynomial is a number, the degree of a polynomial is some lovely vector in z to the r. B is now no longer the maximal ideal, it's some ideal, some monomial ideal, and we call the irrelevant ideal because we are going to throw it away when we construct our formula. Doesn't matter. Yeah.
So on this one, you can have torsion, right? So you have to assume that the toric variety has no torus vectors.
Sure. Say we're smooth or work on the stack. Whichever. Work. Assume generally that I'm saying things that can be made correct. So B is the irrelevant ideal. It's the ideal of my fixed locus. Right? If we have x inside of y, we get some z to the r graded ideal. Or maybe s of x, which is just the quotient, that's not ix. And again, we get some m, a z to the r graded S module associated to any coherent sheaf on my toric. And in fact, I'm saying this is a dictionary, but what do I really mean? I mean this is a theorem. Cox from 95. We said, right, there is kind of a correspondence exactly between these two sides of the board. So in particular, if I want to look at things inside of toric varieties, I can translate them to algebra, get multi-graded objects, and ask, do minimal graded free resolutions exist when I'm working in this multi-graded setting? Are they unique? Do they have a good length? And if I say something about their length, can I say something about how many minimal generators of given degrees I have in my resolution? So those are the 4 questions again. So how does the geometry of a toric variety affect the existence, the uniqueness, the length, and kind of the number of minimal generators of a given degree that appear in my free resolution of the corresponding algebraic object here? So what do I mean? Well, it turns out that existence and uniqueness, again, come from a theorem that's already on the board. But let me write it again just to draw attention to the differences in these cases. So here, when I was working on projective n space, I said if m comes from something on Pn, we get it bound by the dimension. Now I'm always going to assume that m is a module coming from a coherent sheaf on some toric variety y constructed in this way. Here Hilbert in 1890, z to the r graded resolution exist and are unique isomorphism and the length of my free resolutions here is going to be bounded above by the dimension of y. So far, so good. Plus the rank of the Picard group of y. Minus 1. Not so good. So where is this coming from? Well, in this construction, I took a torus of dimension n plus 1 and quotiented it out by something of dimension r. So my toric variety should have dimension n minus r. And essentially, we don't see, that means the homogeneous coordinate ring exactly has, n is exactly this number here, essentially. When we were working on projective space, we didn't see this Picard rank show up and this minus 1 show up because, well, this was 1 for projective space, 1 minus 1, 0, let's ignore it. But on other toric varieties, that's not the case, right? If you work on a product of 10 million P1s, I don't know why you're doing that, but maybe you have a reason to. The rank of the Picard group is going to be 10 million, and that's going to be really big and make your resolutions much longer than they want to be. This poses often fundamental challenges. This is bad. The rank of the Picard group of y bigger than 1. Our resolutions become too long, and our dictionary between nice geometric properties and nice algebraic properties go out the window. And I should note here, for those, just to make the connection clear, z to the r is exactly the smooth setting Picard group of my toric variety here. So when I'm saying things are z to the r graded, I'm really saying they're graded by the Picard group of my toric. So already we see some good things, minimal free resolutions exist and are unique. Very bad thing, they're too long. Let's see if we can control the number of minimal generators that appear in given degrees in them, so the height. To do that, we need a definition. In 2004. Which says if y or f is a coherent sheet on toric variety y, and d is some vector inside of z to the r, which I'm associating with the Picard group of y, and f is d regular if and only if the higher cohomology of f twisted by E vanishes. So I have to tell you what E is. E is going to be over some infinite region, Li of D, inside the Picard group of Y. If we check that the cohomology vanishes in some region that they define, Li of D, inside the Picard group for all I greater than or equal to 1. So we have to look at this cohomology vanishing in some big region inside the Picard group. And this is the definition of what we might say multi-graded Castellan over Mumford regularity on a toric system. So what are these Li of D regions look like? You should think it looks like summing over all vectors. When I sum the coordinates, we sum to I of D minus D plus F cone of 1. So somehow it's a bunch of translates of cones in which we have to keep track of our vanishing. If we wanted to make this a little bit more clear, let's just look at what this would say in the case of a product of projective space. example, y Pn1, Pn2, when you take D, the origin, what do these regions look like? Well, L1 has 2 corners here at -1, 0, and 0, -1. We want to ask that H1 vanishes in all twists in this region. H2, we need to ask vanishing in a slightly larger region. That's 3 corners, -2, 0, -1, -1, and this one. So this would be L2 region, and this is where H2 needs to vanish. So it's kind of these regions with many corners going off into different directions. Because we really want to ask that our cohomology vanishes. And this is a beautiful definition. It makes almost everything you would want to be true, true. You get things like consistence. In fact, you can check this on a finite number of points. Many things are great, and it's a very fantastic, very thoughtful definition, I would say. It's right. However, it turns out that just as Hilbert's syzygy theorem doesn't provide a strong relationship between the syzygies of things in toric varieties, it turns out regularity in this multigraded sense of Ryan and Greg doesn't provide a tight relationship between the height of resolutions or the degrees that appear in resolution. So in particular, Eisenbud-Godot fails in the following sense. A fact, won't prove, but I'll just state it as a fact. The degrees, the syzygies, N1 plus Pn2 do not determine the regularity in some precise sense. So what do I mean? I mean, there are 2 nice modules living over a product of 2 projective spaces, such that their syzygies, their multigraded Betty numbers, are different, but their regularity is the same. But somehow this relationship where syzygies and regularity are exactly related breaks down. It's not completely unsalvageable. There is a bound, so there have been a number of different bounds. Plagen and Smith gave a relationship of how you can bound some of the degrees in terms of regularity and vice versa. Chardin has worked on this also. So there is some relationship, but it's not very strong, I would say. And I would say the failure of having resolutions of the right length and of the right height somehow inspired mathematicians to say maybe minimal graded free resolutions were the wrong thing to look at. What do I mean by that? Well, maybe we shouldn't be saying we want to look at things that are minimal graded free resolutions. We want to look at things, something else. And what was that? Well, in 2017, and Smith used the following definition. Short resolution. N is a complex F dot EWR graded 3 modules such that when I take the corresponding complex of sheaves, this is a resolution line numbers of the sheaf corresponding to N. So, put differently, that F is just a complex. I've made no assumption about it being exact anywhere, other than to say, when I look at the complex of sheaves associated to it, it resolves the associated sheaf. So,
Okay, there's an R missing. Okay.
What?
I was confused. There's one word is mistake. R resolutions of the three layers.
yeah. So it's not. Okay, so notice F is not necessarily exact. Instead, the homology of F is supported exactly on the irrelevant idea, because when I take the complex of sheaves, the homology has to vanish, which means it has to be supported on that part that we don't care about. So somehow we're allowing homology, but not too much. And the second thing is we call a virtual resolution short if the length is bounded above by the dimension of the toric variety we're working on Y. So somehow they introduced this idea and said, well, maybe we can weaken our definition, allow some homology, and get short virtual resolutions. So the conjecture then becomes short resolutions exist. Conjecture. Smith. I think paper, they introduce these. Virtual resolutions. This for all smooth projective toric varieties. And why would we want this? Well, this would help say give a new kind of algebra geometry dictionary where we start to get things that are tighter, or we've always replaced minimal resolutions with virtual resolutions. Of course, we now have to ask the questions, do virtual resolutions exist? Do short virtual resolutions exist? Are they unique? If they exist, we know their length is bounded in the right way. What about kind of what twists appear in them? Well, I'll note from the definition, virtual resolutions are definitely not unique, because you can always just take a different module that sheafifies to the same sheaf and take two different resolutions. You can always do that by taking high enough truncations in different degrees or adding irrelevant things. So somehow virtual resolutions are inherently, from their definition, non-unique. You might hope that short resolutions, if they exist, are unique, and that's sadly not true, but we do have that at least they exist. The theorem, Goethe and Smith, 17. Short virtual resolutions exist. And Y is a product of R projective spaces. So when you have a product of projective spaces, virtual resolutions exist and are short. Great. Pretty limited. How does the proof go for this? Well, they give a few different proofs of this fact, but the main one, I would say, is constructed in the following sense. So let's let Y be this product. You consider the product of Y with itself, and we're going to play a little push-pull game. Two projections here. We take sheet M, you're going to twist it sufficiently by some D. Not at all clear what we do here. Then we want to pull back along pi 1. Of n twisted by D. And then it lives on the product of y with itself. And now I'm going to tensor this with the resolution of the diagonal inside of y cross y. So what do I mean? I mean there's an explicit resolution they write down in the sense of a free resolution of the diagonal in y cross y. You can tensor that by that complex. And lastly, you want to push this all forward, but now I'm tensoring the complexes. So now, I'm sorry, folks, we got to do the right direction. And this is when you take global sections, the short virtual resolution they construct. Great. Have fun writing this down. Yes.
Is it okay that in my head a little free Vokai lamp is linked?
Yes, this is exactly
Okay.
a Fourier Mukai type construction. So
Okay.
you should be thinking Fourier Mukai if you want to say those words. So they give other constructions that are more explicit than this, but I always found this construction both nice because it has the Fourier Mukai-like linking and not so nice in that if I ever asked you, hey, what is this virtual resolution? I struggle to write down Fourier Mukai transforms as actual complexes on the nose. And this got my co-authors and myself thinking. And we said, well, Eisenbud and Goethe failed from this fact, but there was a third part of Eisenbud-Goethe, namely, deregularity could be measured by the truncation having a linear resolution. And maybe that doesn't fail. Okay, so theorem. Myself, Warren Franson Howard, and Maru in 2022. If we're still in the setting of a product of projective spaces, and we take some D and Z to the R, then the sheaf M is deregular, turns out is equivalent to the truncation of the module D. So looking at the submodule generated by everything degree greater than or equal to D, having a what we call quasi-linear so in some sense the context of the first part of the theorem is what do I mean by quasi-linear? What I essentially mean is that the degrees of the ith step are in the region Li minus 1, minus 1. So take the vector D, we shift it by the all ones vector backwards, so kind of, and we look at the thing that has exactly I form. So this is somehow a slight weakening of having a linear resolution that detects regularity on the nose.
So what is Li minus 1?
Li minus 1 is, I did, so it was the region coming from the Fagen-Smith's definition of regularity. So essentially it's the region with I corners instead of I plus 1 for regularity. So great, but why am I putting this in conversation with this result of Torkesher and Smith? Well,
I have another question. Does this also work in the long old-fashioned resolution?
this is by this I mean a quasi-linear
This is the long old-fashioned.
minimal resolution.
Minimal resolution.
Minimal free. Sorry. Good question. Sorry for being imprecise. Minimal free resolution, but in fact, being quasi-linear in this case implies that the minimal free resolution of M truncated at D is a short virtual resolution of M. When you unpack what the definition here is, you exactly say, oh, in fact, the resolution, the minimal pre-resolution, the old-fashioned kind of this truncation is a virtual resolution, and it's short. That it's virtual, not so hard. Truncating a module in low degree doesn't change the sheet associated to it. So this is great. I want to end by saying briefly a couple words about how we go about proving this. I'm just going to sketch it very broadly. I only have 5 minutes left. So the proof here has 2 steps. A nice short proof. Let's call this resolution deconstruction. Burkish domains that G. So the first step is to show that the degrees of the resolution, I guess I mean the minimal free resolution of this truncation, M truncated at D, are exactly equal to the degrees appearing in the BES construction of G. So whatever this Fourier-Bucay transform type thing is, the syzygies that appear in the truncation here are the same as the syzygies that appear in G. So this is the first step. And why does this matter? The second step is to relate regularity to vanishing of syzygies G. And well, remember, regularity is defined in terms of some cohomology vanishing. And here I've tensored some resolution of the diagonal that has a bunch of cohomology things in it. And so it's not so hard that the second step might be true. And so in particular, you say, oh, being regular implies vanishing on G implies vanishing on M, truncated at D. You essentially back solve for the definition of quasi-linear, and you then see that it falls out for free. But you're now presented with an interesting thing. I now have 2 types of resolutions. A minimal graded free resolution on the nodes of the truncation of M, and a virtual resolution of M. This one, a priori, might have homology. This one doesn't. They have the same Betty numbers. When you sheafify, they resolve the same thing. Are they the same? If you're on projective space, of course, minimal free resolutions are unique. Make a little argument. You get this. But it turns out that virtual resolutions aren't unique. And so proving this to be true is much harder. In fact, 2 years later, in the theorem I'll end on, you needed to prove a fairly strong but limited uniqueness results. So like myself, Lauren, and Ruth in 2024, although in the same paper that was originally posted in 22. So let I be a forthright with E1 ET, a full sectional collection. Line bundles, so some line bundles generate the derived category in a nice way. If dot and G dot multiple resolutions of the same module M built from the EIs then F dot is isomorphic to G. So somehow virtual resolutions built on four varieties from full strong exceptional collections are in fact unique. And well, full strong exceptional collections don't always exist, but they do on a product of projective space, showing that the Burger-Sherman-Smith construction and ours agree on the nose, and in fact, this provides a nice uniqueness result in a number of limited other settings as well. And so I'll end here. Thank you so much.